Have you ever thought about that invisible force that's literally keeping your feet on the ground right now? The one that keeps the moon from flying off into space and makes all the planets dance around the sun? Well, that's gravitation. It's like the master architect of our entire universe. So, let's jump right in and figure out how it all works. It all starts with a super simple observation. Something so normal, we don't even think about it. You drop an apple, and it falls down. Obvious, right? But believe it or not, that simple little act holds one of the biggest secrets of the cosmos. Because here's the real puzzle. If the Earth is pulling that apple down, why isn't it pulling the moon down too? Why does the moon just hang out up there night after night, circling us? Answering that question, well, it changed everything we thought we knew about the universe. So here's our game plan for this explainer. We're going to start with that classic story of the apple and the moon. Then we'll uncover the universal rule that connects everything. We'll see how gravity affects us right here on Earth, clear up that whole mass versus weight confusion, solve the riddle of why huge ships float, and finally, we'll just step back and admire gravity's amazing grand design. Okay, so our story begins with the man himself, Isaac Newton. You know the legend. He's just sitting there, sees an apple fall from a tree, and suddenly a light bulb goes off. He looks at the apple on the ground, then he looks up at the moon in the sky, and he asks this brilliant question. What if the force pulling the apple down is the exact same force that's pulling on the moon? This was the big aha moment. Newton realized there aren't separate rules for stuff on Earth and stuff in the heavens. It's all one giant system, playing by the same rules. And get this, the moon is falling towards the Earth all the time, but it's also moving sideways so fast that it constantly misses us, curving around our planet in what we call an orbit. Wait, falling forever without ever hitting the ground? How does that even work? It sounds kind of impossible, doesn't it? Well, don't worry. Let's try a simple little analogy to really get a feel for how orbits happen. So I want you to imagine you've tied a stone to a string and you're whirling it around your head. As long as you're holding on, that stone is going in a nice, neat circle. But the second you let go, poof, it doesn't keep circling. It shoots off in a perfectly straight line. So what was forcing it into that circle in the first place? The string. Your hand was constantly pulling the stone inward, toward the center. That pull was the only thing stopping the stone from going straight and instead bending its path into a curve. This center-seeking force has a proper name. It's called centripetal force. For our stone, the string was providing that force. Now let's go back to the moon. Obviously, there's no giant string connecting the Earth and the moon. So what's the invisible string? You guessed it, it's the Earth's gravity. And this is where things get truly mind-blowing. Newton figured out that this force isn't just between the Earth and the moon. It's universal. Every single thing in the universe, with mass, pulls on every other thing. You, me, the Earth, distant stars, we're all part of this huge, invisible web of attraction. How cool is that? So how does this whole thing work? Well, there are two main rules. Rule number one, the force depends on mass. Basically, how much stuff an object is made of. The more massive the objects, the stronger they pull on each other. It's why you feel the pull of the giant Earth, but not the pull of the person sitting next to you. And rule number two is all about distance. Gravity is super sensitive to how far apart things are. It follows something called an inverse square law. The best way to think about it is like spray paint. Spray close to a wall, you get a small, thick dot. Move farther away, and the same amount of paint spreads out over a much bigger area, so it gets way thinner. Gravity is just like that. Double the distance, and the force drops to 1/4 of what it was. And when you put those two ideas together, mass and distance, you get this one beautiful equation. F is the force of gravity. M and M are the masses of the two objects, and D is the distance between them. And that G, that's just a special magic number called the gravitational constant that makes the math work perfectly anywhere in the universe. Okay, we've been talking big, cosmic stuff, but let's bring it all back down to Earth. How does this law actually apply to things falling right here in our backyard? So when an object is falling, and we can pretty much ignore things like air resistance, we say it's in free fall. And here's the cool part. Objects in free fall don't just fall at one speed, they accelerate. They get faster and faster at a very specific, constant rate. Now get ready for an idea that might feel a little weird at first. The rate at which things accelerate has absolutely nothing to do with how heavy they are. No, really,
If you were in a vacuum, a place with no air, and you dropped a feather and a bowling ball at the same time, they would accelerate at the exact same rate and hit the ground together.
And that constant rate of acceleration here on Earth has a special value. We call it g, and it's about 9.8 meters per second squared. What that really means is that for every second an object is falling, its speed increases by 9.8 meters per second. It's like the steady drumbeat of gravity on our planet. Understanding g is the key to clearing up something that confuses a lot of people. In everyday life, we use the words mass and weight like they're the same thing. But in physics, they are totally different, and it's all because of gravity. Let's break it down nice and simple. Your mass is the actual amount of stuff you are made of. It's measured in kilograms, and it is the same no matter where you go in the universe. Your weight, however, is the force of gravity pulling on your mass. And since g, that acceleration, is different on different planets, your weight can change. And here's the perfect example to make it stick. The moon is much smaller than Earth, so its gravity, its g, is much weaker. So if you could stand on the moon, you would weigh only 1/6 of what you do on Earth. But your mass, the amount of you, would be exactly the same. You just feel super light and could probably do some amazing jumps. Okay, time for another fun puzzle that seems to completely defy gravity. We know gravity pulls things down, so how can a massive ship made of thousands of tons of steel just float so easily on the ocean? I mean, really think about it. If you drop a tiny steel nail into a glass of water, it sinks right to the bottom. But a giant ship made of the same stuff just cruises along. What's the secret? Well, it turns out there's another force pushing up. The answer comes from the amazing Archimedes principle. It says that when you put something in water, the water pushes back up with a force called the buoyant force. And the strength of that upward push is exactly equal to the weight of the water the object pushed out of the way. A nail displaces almost no water, so it sinks. But a ship's huge hollow shape displaces a massive amount of water, creating a huge upward force that's strong enough to hold up its entire weight. And this principle is super useful. It's not just for ships. It's exactly how submarines work. They control this buoyant force to dive and surface. It's even the science behind little instruments that can check if milk is pure or measure how dense different liquids are. So as we wrap this up, let's just take a moment to appreciate the huge journey we've been on. We started with a simple, falling apple, and from there, we've managed to understand the very mechanics that run our entire solar system. What Newton did was incredible. He gave us a single, elegant law that explains everything from why we stay on the ground, to the moon's orbit, to the paths of all the planets, and even the rising and falling of the tides. It's the one force that ties our whole cosmic neighborhood together. And I want to leave you with one final awe-inspiring thought. In all of physics, there are 4 fundamental forces. And you know what? Gravity is the weakest one, by far. It's trillions of times weaker than the others. And yet, it's the force that builds the biggest things in the universe. It creates stars, solar systems, and it holds entire galaxies together. So what does that tell you? That our universe is shaped not by the strongest, loudest force, but by the one that is the most patient, the most persistent, and has a reach that you just can't escape.